Scene script. Have you ever pondered how satellite internet like Starlink works? We're about to unravel this space-age wonder. Imagine a world where high-speed internet is no longer a luxury exclusive to urban areas, but a universal right that even the most remote corners of the globe can enjoy. That's the promise of satellite internet, and it's a game changer for those locations that traditional cable and fiber optic networks can't reach. Let's start with the basics. Satellite internet is a form of wireless communication that uses satellites to provide internet connectivity. It's a bit like how your television can receive signals from space, but instead of bringing you the latest episode of your favorite show, it's delivering emails, streaming videos, and supporting all your online activities. Now you might be wondering, what makes Starlink a noteworthy player in this arena? Starlink is a satellite internet service provided by SpaceX, the aerospace company founded by Elon Musk. They have a vision to provide affordable, high-speed internet across the globe, and they're doing this by launching thousands of small, low Earth orbit satellites, also known as LEO satellites. These satellites are closer to Earth compared to traditional geostationary satellites, reducing the time it takes for data to travel back and forth. This means faster internet speeds and lower latency, which is the delay between a user's action and the internet's response. In essence, Starlink is aiming to bridge the digital divide and bring the internet to the places that need it most, from rural communities to disaster-stricken areas. It's a lofty goal, but if anyone's equipped to make it a reality, it's SpaceX. Let's dive into the depths of this fascinating technology. Not all satellites are created equal. So, what sets Starlink apart from traditional broadcast satellites? Well, let's get into it. Traditional broadcast satellites are typically placed in geostationary orbit, about 22,000 miles above Earth. They stay in the same spot relative to the Earth's surface, making them ideal for broadcasting television signals. However, this distance means there's a noticeable delay when using them for internet service, which is a significant drawback for real-time applications like video calls or online gaming. On the other hand, we have Starlink, Elon Musk's brainchild. Starlink satellites occupy a much lower orbit, only about 340 miles above our planet. This proximity dramatically reduces the time it takes for data to travel back and forth, thus eliminating the latency issues associated with traditional broadcast satellites. Yet, there's a twist. Because of their lower orbit, Starlink satellites move relative to the Earth's surface. This means they can't provide coverage to a fixed point on the ground all the time. To solve this problem, Starlink uses a vast network of satellites with thousands already in orbit and many more to come. This network ensures that as one satellite moves out of range, another one moves into place, providing seamless, continuous internet coverage. This is quite different from traditional broadcast satellites, which typically number only a few dozen and stay fixed over one specific region. But the Starlink advantage doesn't end with just low latency and continuous coverage. Each Starlink satellite is equipped with lasers that allow them to communicate with each other. This inter-satellite communication makes the Starlink network more resilient and efficient, as data can be relayed through multiple paths, reducing the chance of service interruptions. In conclusion, Starlink's lower orbit, higher satellite count, and inter-satellite communication set it apart from traditional broadcast satellites. This difference in approach is what makes Starlink's internet service unique. Now, let's dissect the parts of Starlink's user terminal, affectionately known as Dishy McFlatface. This is no ordinary dish. It's a high-tech piece of equipment that's packed with innovative technology. At the heart of Dishy McFlatface is the aperture-coupled patch antenna. It's a fancy name, isn't it? But what does it do? In essence, this antenna captures and transmits signals, allowing Dishy to communicate with the Starlink satellites hovering in space. Imagine the antenna as a busy airport control tower, constantly receiving and sending out information to aircraft, ensuring smooth travel and safe arrivals. Similarly, the aperture-coupled patch antenna sends and receives data to and from the Starlink satellites. But let's delve a little deeper. The antenna is composed of numerous tiny patches, each acting as a mini antenna. Together, they form an array, hence the term array antenna. These patches are ingeniously designed to capture a wider range of frequencies, improving the overall performance of the antenna. The beauty of this design lies in its simplicity. Each patch is small and relatively easy to manufacture, yet when brought together, they form a powerhouse of communication. The antenna array is further coupled with an aperture, a hole or an opening if you will, which allows the electromagnetic waves to pass through. This coupling enhances the antenna's ability to capture and transmit signals, making it a vital part of the Dishy McFlatface. But it doesn't stop there. The antenna is backed by a network of electronics that process the incoming and outgoing signals. This includes amplifiers to boost the signal strength, filters to remove unwanted noise, and converters to change the signal from analog to digital and vice versa. Together, these components ensure a seamless flow of data between the Dishy McFlatface and the Starlink satellites. This piece of technology is what allows Dishy to connect with the satellites in space. Ever wondered how Dishy communicates with satellites thousands of miles away? The answer lies in electromagnetic waves. Picture this. Invisibly zipping around us at all times are countless waves of energy. These are electromagnetic waves, a type of wave that includes visible light, radio waves, microwaves, X-rays, and more. Each type of wave varies in its wavelength and frequency, but they all share one thing in common. They travel at the speed of light. So, how does Dishy use these waves? Well, Dishy makes use of a specific type of electromagnetic waves known as microwaves. These work particularly well for satellite communication because they can pass through the Earth's atmosphere without being absorbed or reflected. Here's how it works. Inside Dishy, there's an electronic component known as an amplifier. This amplifier generates an electrical signal. When this signal is fed into Dishy's antenna, it creates an oscillating electric field. This field generates an electromagnetic wave which races off into space at the speed of light. But the story doesn't end there. These waves aren't just randomly thrown into space. They're precisely directed towards the Starlink satellites. How? Through a process called beamforming, but we'll dive into that in the next scene. One more thing to note. The data that Dishy sends and receives isn't carried in the wave itself. Instead, the wave acts like a carrier, with the data superimposed onto it. This is done through a process called modulation. Think of it like a cargo ship carrying containers. The ship is the wave, and the containers are the data. The power of electromagnetic waves lies in their speed and their ability to carry information across vast distances. They're a fundamental part of our modern world, enabling everything from radio broadcasts to mobile phone signals, and of course satellite internet. These waves are the lifeline of Dishy's communication with the Starlink satellites. Now let's delve into the world of beamforming and beam steering, the two key technologies that make Starlink possible. First things first, what is beamforming? Beamforming is a signal processing technique used in sensor arrays for directional signal transmission or reception. In simpler terms, it's like tuning a radio to a specific station, except in this case, the radio is the Starlink dish, and the station is a satellite. However, instead of tuning into a frequency, we're focusing an electromagnetic wave into a beam. In the context of Starlink, beamforming is used to create a focused, high-gain signal. This is achieved by controlling the phase and amplitude of the signal at each antenna in the array, which we can think of as the speakers on our radio. By adjusting these factors, we can form a beam of energy that is highly concentrated in a specific direction. This is extremely useful for Starlink, as it allows the dish to communicate with satellites hundreds of kilometers away in space. Now, on to the second part of our topic, phased array beam steering. This might sound complex, but it's really just a fancy way of saying directing the beam. In Starlink's case, we're directing the beam towards a satellite. Phased array beam steering is a technique used to electronically steer the direction of an antenna beam. It works by changing the relative phase of the signal at each antenna in the array. By adjusting the phase, we can change the direction of the beam without physically moving the antenna. This is crucial for Starlink, as it allows the dish to maintain a connection with a satellite even as it moves across the sky. In the case of Starlink's Dishy McFlatface, the antenna is made up of hundreds of tiny elements, each capable of transmitting and receiving signals. By controlling the phase and amplitude of the signal at each element, Dishy can form a beam and direct it towards a specific satellite. And, as the satellite moves, Dishy can electronically steer the beam to follow it, maintaining a stable, high-speed internet connection. So that's beamforming and beam steering in a nutshell. Two technologies that, while complex, are the backbone of Starlink's revolutionary satellite internet service. These technologies enable Dishy to maintain a continuous connection with the Starlink satellites. So, we've got a beam, but how does data travel within it? Well, let's dive into it. The method Starlink uses to encode data onto the beam is called 64 QAM, or 64 quadrature amplitude modulation. This might sound like a mouthful, but it's actually a common way to transmit data in modern telecommunication systems. Imagine a courier who has to deliver packages. Now, instead of delivering one package at a time, he decides to stack multiple packages onto his hands, under his arms, even on his head, all to deliver more packages in one trip. That's essentially what 64 QAM does with data. In simpler terms, 64 QAM is a method of combining multiple bits of data into a single symbol that can be transmitted. This is done by varying the amplitude and phase of the signal. The 64 in 64 QAM indicates that it can encode 6 bits of data into one symbol, which means it can represent 64 different states. Now imagine a grid of squares, each square representing a unique state. 64 QAM fills up this grid with 64 squares, each corresponding to a specific combination of amplitude and phase. The way this works in Starlink is that the data to be sent is first broken down into chunks of 6 bits each. Each of these chunks is then mapped to a unique state in the 64 QAM grid. This state, represented by a specific combination of amplitude and phase, is then encoded onto the beam. The beam carrying these symbols then travels all the way up to the Starlink satellite. The satellite receives the beam, decodes the symbols back into bits, and sends the data on its way to the internet. And there you have it. The beam, once a simple carrier of light, is now a complex highway of information, bustling with data zipping back and forth between Earth and space. This process is how your internet data makes its way to space and back. To wrap things up, let's talk about the size of the Starlink Dishy and the electromagnetic waves it uses. The Starlink Dishy, affectionately known as Dishy McFlatface, is not your average satellite dish. It's a sleek, modern marvel, just under 2 feet in diameter, about the size of a large pizza. It's designed with a flat, circular shape to facilitate a wider range of communication with the overhead satellites. This compact size is a testament to the brilliant engineering behind the Starlink project, making it possible to deliver high-speed internet from space to just about anywhere on Earth. Now let's dive into the world of electromagnetic waves. The Starlink Dishy operates in the Ka and Ku bands of the microwave portion of the electromagnetic spectrum. The wavelengths in these bands range from just under 1 centimeter to just over 2 centimeters. These short wavelengths are crucial to the functionality of the dish. They enable the transmission of large amounts of data at high speeds, which is exactly what's needed for broadband internet service. However, these wavelengths come with their own challenges. They can be affected by atmospheric conditions like heavy rain or thick cloud cover, which can disrupt the signal. But the Starlink engineers have thought of this too. The system includes advanced algorithms to mitigate these effects and maintain a reliable connection. In essence, the Starlink Dishy is a perfect blend of size and technological prowess. It's small enough to be installed on a rooftop or balcony, yet powerful enough to communicate with satellites thousands of miles away in space. The electromagnetic waves it uses are short enough to carry vast amounts of data, yet resilient enough to withstand the challenges of Earth's atmosphere. Understanding the size and scale of these components gives us a better appreciation of this technological marvel. Now that we've journeyed from your home to space and back, let's wrap up our exploration of how Starlink satellite internet works. We began our voyage by delving into the enigmatic realm of satellite internet, peeling back the layers of complexity to reveal a world of technological marvels. We discovered that Starlink satellites are not your average broadcast satellites. Instead of hovering in a fixed position, these satellites form a constellation that orbits the Earth, ensuring global coverage. This fundamental difference allows Starlink to provide reliable internet connectivity to even the most remote corners of the world. In the heart of your Starlink setup, we found the quirky Dishy McFlatface. This is not just a dish, it's a sophisticated piece of technology packed with components designed for a singular purpose, to communicate with satellites thousands of kilometers away. At the core of Dishy is an aperture couple patch antenna, a marvel of engineering that takes electromagnetic waves and turns them into a focused beam of data. This led us to the concept of beamforming, a method that allows Dishy to form a beam that reaches space. It's like having a conversation in a crowded room. You don't yell to be heard, you focus your voice towards the person you're talking to. That's essentially what Dishy does. It concentrates the electromagnetic waves into a beam, directing it towards the Starlink satellite. Steering that beam is another feat altogether. Dishy sweeps the beam across the sky, following the Starlink satellite as it moves. This is achieved through phased array beam steering, a technique that enables the beam to be electronically steered, providing a seamless connection. We then embarked on a data journey, understanding how information is sent and received. The process involves encoding data onto the beam using the 64 QAM method, then sending it to the Starlink satellite. The satellite then sends the data back to Earth, completing the loop. Finally, we visualized the actual size of the Starlink Dishy and the electromagnetic waves it deals with. It's intriguing to think that this compact dish handles waves that are much larger than itself, yet it does so with an efficiency that is quite astounding. And there you have it, a glimpse into the fascinating world of satellite internet, a marvel of modern technology, bringing the world closer together one satellite at a time.